So section 4.3, we're going to be taking a look at Riemann sums and definite integrals, and I really hope you've printed out your notes, because those of you who haven't printed out your notes are not going to want to write everything down that's on this page. So I'm just going to let you see my notes? There's a lot of writing. We're not going to take the time to write every word down, okay? So even if you like to take your notes mostly by hand, this one's probably not one you want to do that for, so you may want to print this out later. But we're going to talk through it, so if you want to write down parts of it, that would be fine. Riemann sums. So let's talk about what these are. So we're going to let a function be defined on an interval AB, and delta x be a partition of AB. So that's what we did last time. We partitioned things into interval pieces that were 1/2, is the one that I did in class. The A value for the start, the B value for the end, correspond to x0 at the start and xn at the end. And delta of x sub I is the width of the ith subinterval. Now, while we did it to be very careful and made all of our intervals the same width because it made it easier to do calculations, you don't have to have the widths actually the same for the process to work, which is very interesting. So when you see this talking about the delta x sub I being the width of the ith subinterval, those could all be different widths. All right, like we liked the fact that they were the same, at least I did, because we could pull out the different that piece of it and do all the addition together, and then multiply by the 1/2 because they all had a 1/2 width. But it works even if they aren't the same width. Excuse me. If c sub I is any point in the ith subinterval, so we used the left-hand endpoint, we used the right-hand endpoint, and we used the midpoint. But this is telling you can use any height you want. Any value in between x sub I and x sub I plus 1. Anything in between you can use for the height. Doesn't matter. It's making things very arbitrary, right? Very generalized. Then the sum from I equal 1 to n of f of c sub I times delta x sub I. We saw that notation last time. This is the height times the width. That's what you're seeing happen here. For each interval is called the Riemann sums of f for our partition delta. The sums that we did in section 4.2 were examples of Riemann sums, but there are more general Riemann sums than those covered there as well. Okay, so we just messed up everything that made 4.2 easy. That's really what we did. Did you guys catch that? Yeah, totally. All right. It'll all come together. Just bear with me. A definite integral. Now, you've seen the word integral before. We saw it back in section 4.1. We used integral, we used integral when we talked about a general antiderivative. I used the word integral, I used the word antiderivative interchangeably. So this word definite integral is now showing up, but it's showing up in reference to summations, not in reference to antiderivatives. So if f is defined on that closed interval, and the limit of the Riemann sums over the partition delta, so the limit as delta approaches 0 of the summation of x equal 1 to n of f of c sub I times delta x sub I exists as described above. In other words, if we have this thing we created up here, and what we're doing is adding this limit at the beginning. Now the limit at the beginning is telling you that the delta, how wide it is becoming infinitely small. That's what it's saying. All the widths are becoming very, very, very thin. Okay? And if that limit exists, then we say that f is integrable. It has an integral on AB. And in particular, this limit is equal to that antiderivative that we found with one difference. There's something about this that looks a little different than we did before. Do you notice what it is?
The A and the B.
The A and the B. Okay. So this A and this B are showing up. Don't really have a good reason for that quite yet. We know what the A and the B are. They're the beginning and the end of my interval. I mean, we know what they are. It's already been defined that way. But this idea of this antiderivative, and I actually have these numbers that sort of tell me where I start and where I stop, are showing up. This limit is called the definite integral of f from A to B. The number A is the lower limit of integration, and the number B is the upper limit of integration. I promise I'm going to show you how it all works with some examples. We're just doing all the notes parts first. So just like when we did limits and then we did derivatives, we did some different theorems along the way, we have these questions about when things exist and also when things are continuous and how continuity plays into that. So our next theorem actually talks about the connection between continuity and integrability. So if a function is continuous, right, you can draw it without picking up your pencil. That's sort of a visual picture of what continuous means. On the closed interval AB, then f is integrable on AB. Okay? So over here, the thing on the left, we learned back in section 4.2, talked about finding area under a shape, and now we are actually taking those pieces and we're making those rectangles infinitely narrow, right? And we're saying that they're going to equal this antiderivative that we have found back in section 4.1, and somehow the endpoints matter with what's going on. And it's interesting because what this actually tells you is you don't have to necessarily have it differentiable. You do need to have it continuous. Only continuity matters. So you could have sharp turns. That would be okay, right? But you can't have jumps or asymptotes or holes because those are things that defy or break apart the continuity. Okay? And I think this is our last one for some examples, indeed. All right. Theorem 4.5 says that the definite integral is the area of a region. So if f is continuous and non-negative, we do need the non-negative, on the closed interval AB, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines A and B is the area that's the integral from A to B of f of x dx. And I'm going to show you, there's one more definition later that talks a little bit more about this. But our visual picture that we're getting from what we're doing here is, I'll use that same graph that I had before. It looks something like this in section 4.2. Actually, we started at 0 and we went to 1. So it looked like this. It went from 0 to 2. And what we've actually are finding is we're actually using these rectangles, infinitely small rectangles. And now we're going to use the antiderivative instead of the infinitely small rectangles to do this. And we're going to actually find that area exactly. It will not be an approximation. It will be exact. And we're using antiderivatives to do it. Now, before we get to that, we have a couple of pieces that we're going to take a look at for this. So I don't know that I have this written down. So hopefully, does anybody have the pages from their book with them? Anybody at all? Oh, Zach does. I need page 273.
273.
Yep. Page 273, and I'll show you what the picture looks like if I can take a picture of Zach's paper. Oh, that'll work even better. Thank you, Olivia. Thank you, Zach. So page 273. Oh, I said 273. I think it's not. I think this is an old edition of a book. Try problem number 16 in 4.3. Do you see problem 14 or problem?
Yeah. That makes a bit more sense.
Yeah, that will make it more sense. Okay, let me take a picture and put this on this slide. Well, actually, let me just sketch it. That'll work. This is actually supposed to be page 277. So adjust your notes. This is page 277, not 273.
Number 16.
Number 16. So page 277, number 16, and the picture looks like this. So I'm just going to sketch the picture. I'm afraid if I leave my screen, it might stop my video, and I don't want it to split the video. So we have this picture. The graph looks something like this-ish. Kind of like the one I just drew, but it's actually hitting the y-axis and the x-axis, the origin. It's going sort of in a, I'll do it dotted down to here, and it's shaded in. That's too wide. Through here is shaded in. It tells you that the equation is x squared. It tells you that this cap is 4 and it's got it all the way down to 0, and that the interval down here is 1 to, and then I've got 2. So I think that's enough of the pieces of information. Thank you, Lulia, for it to be filled in. So you're going to be doing, if for those of you who do have that page, you're going to be doing some questions that actually start out looking like this. All they are is they draw a picture, okay? They've got a picture given to you, and all you're asked to do is to set up the notation. You can do that. You're not solving anything, you're just setting it up. That's where we're starting. Can you do that?
Like a gateway.
Yeah, like a gateway, but it's easier than that, because in the gateway you actually are finding an antiderivative. We're not even going to do that on this problem. We're just going to set it up. So this notation over here that we keep seeing showing has that script s at the beginning and the dx at the end. So all of ours will as well. Okay, so we're going to have a script s, and we're going to have the dx. In between them is the function that we're given. Well, this function is x squared. Okay, so far so good. And then the a and the b are the endpoints of the shaded in area. So always x values. So what is the x value on the left's endpoint for this shaded region?
0.
It's 0. So we put 0 as the lower limit. The lower limit always goes on bottom. And then how far to the right do we go? 2. And is all this question is asking.
I have a question.
Yep.
If y equals x squared, then why is it in the integral? Why aren't we using the derivative? Because it has a dx.
The dx at the end right here is telling you what the, so this is a derivative. It's telling you this is a derivative. And we're going to try and find its original function, right? This part right here is telling you what the variable is in your function. And I know that that feels like it's silly right now, but the time will come for those who do move on far enough in calculus where you'll have multiple variables within the function and you need to know which one you're actually considering the variable at that moment. So for the purposes of our discussion right now, it's sort of like having the end of a parenthesis where the beginning of the parenthesis is the script s. So these will always come in pairs. These will always go together. Yours will always say d of whatever our variable is in the problem. A lot of the times we use x's, but sometimes, WebAssign throws in a u or a t or something, right? W's, it likes to use those occasionally. So whatever your variable is simply going to match the x or the variable at the end.
I mean, what I'm asking actually is like, is the equation not x squared? Like, is it?
So the equation that we are going to find the antiderivative of is y equals x squared.
But that's not the equation of the line.
The equation of what line?
The graph.
Yeah, that's the equation of that graph. It's the black part, not the shaded part, the black part. This is the graph of y equal x squared, right? If I were to look at more of the graph, it would look like all of this. Okay, that's what this graph is. It's y equal x squared. I'm not understanding your question, I don't think. I take the graph that I'm given, y equal x squared, and that's what goes inside of my function. As we actually do the process, because that's not what this question asked us to do, we will take its antiderivative after that. We won't be taking derivatives. Let's chat after class. Okay. All right. There are some shapes that are very friendly. This one's not very friendly if we were actually trying to ask it to find it with some geometric formulas, because it's curved. But some of our shapes actually tell us that they're going to use geometric formulas to find it, okay, before we use the calculus that we need to find other things. So this one's asking us to sketch the region. All right, so sketch the graph using the endpoints given. And then use some sort of geometry instead of calculus to find the area of the shape. So if it's in this section, it's got some kind of geometric formula that you know or have used in the past that you can use. All right, so it's not, pay attention to the directions, because if I ask you a question, I mean, at WebAssign you can't always tell, right? Because it just asks a question and then it's just going to take your answer and it's not going to know how you did it sometimes. True? Yeah. So be careful when I ask on quizzes or tests, because if I ask for it to be geometric and you do it using calculus techniques, you're not following the directions. So be very careful for the directions. This one says a geometric formula. So our equation that we're going to draw is 4. right? It's y equals 4. What does the graph of y equal 4 look like? Oops. Okay, so straight meaning horizontal. Yes, oh, it's a horizontal line. So we're going to draw our axes. I'll use a different color. I'll use blue. And here's the horizontal line. I'm going to call y equal 4. So something like that. And then my interval is supposed to start at 0 and end at 3. So here's the starting at 0, if I sort of think about it as a starting spot. And here's the ending at 3. And I want it to be shaded everywhere in between. So this is the region it's talking about. It's a very basic shape. What is that shape? Almost a square. It's actually a rectangle. Yeah, just because it looks more square shaped on my graph, but it's a rectangle. How do you find the area of a rectangle? Length by width, or base times height, whatever variables you want to think about it as. What are the length and width, or base and height of this rectangle? 3 and 4. So this area is 12. Easy enough?
When you said 12 units squared, or
It's just 12. Yeah, it's just 12. Okay, we're going to do one more. Same thing, same directions. We're going to draw this equation. This is y equals 3x plus 4. What is this a graph of? It's another line. It's not horizontal this time, though, right?
Nope.
So tell me what details we need in order to graph this line.
Y-intercept at 4.
Y-intercept at 4.
Slope of 3.
Slope of 3. So I go over 1 and up 3 to here, and I'm going to go all the way out to 2, so I'm going to do it twice. Over 1 and up 3. So something like that. So if I were to connect my dots, if I drew it well, I didn't draw it great. I'm going to move this over. It looks, oh heavens, try again. It looks something like that. Agreed? But like I said, it starts at 0 and it ends at 2. So the part of the graph that I care about actually is just this part that starts at 0 and ends over here at the 2 value. So I've had this shape shaded in between. This is a basic geometric shape. It's not quite as simple as our rectangle. It is a trapezoid. So let me actually show you how you do it with a trapezoid. That might not be an equation you just remember off the top of your head. But I'm actually going to show you something else you can do if you don't remember the formula for a trapezoid that's actually really nice too. So if you think of this, and it is truly a trapezoid, the area of the trapezoid is 1/2 base 1 plus base 2 times the height. So the base 1 and the base 2 are the two sides that are not equal in length, but they're parallel. They're the parallel sides. So taking a look at this particular shape, one of the sides' heights is really obvious. This one right here, because I plotted the point 4 to start with, right? So one of my bases is 4. What's my other base?
10.
Okay, so I've got 10 and 12. How do we get it? Up 3 twice. Yeah, so we went up 3 twice from my 4. So the other thing you could do is you could actually plug the number 2 straight in here if you want to. That gives me my height. So it is 10, right? The height of that piece, or the length of that piece. So what is the actual height of this trapezoid? 2. It's the other dimension, right? So the bases are the parallel sides. And then the height is the other dimensions, this one, and it is 2. They do. That's nice on this one. That won't always happen, right? Yeah. They do, and so this one actually ends up just being 14. Okay, so that's what it looks like if you think about it as a trapezoid. But I'll show you that you could actually think of it as a different shape if you wish. Oh, you're right. You could think of it as a rectangle and a triangle if you wish. Isn't that clever? That's really all a trapezoid is. So yeah, you could definitely do that. So you could do your rectangle plus your triangle. So my rectangle is base times height, or length times width. And my triangle is 1/2 a different base times a different height. I'm going to go back and call these length and width. I don't want us to think that they're the same, because they certainly aren't. So what are my length and width, Shelby? Yep, of the rectangle, it's 2 times 4. My triangle, I have to work a little bit harder at. One of them is 2, because it's the same as the, yeah, and the other one, this piece would be 6. So 2 times 4 is 8, plus these two cancel like before, and 6, and I get 14. It's very reassuring to get the same answer twice. It's good stuff. All right, so we will continue our discussion next time. It's a very good place for us to stop.